long pronounced bar features, because this particular one has a strong bar in the central region, and it has well-defined magnetic fields and velocity fields, and see a lot of these things in the observations. So other than these optical images, can we actually learn anything from about what's going on in this galaxy? Well, we can derive gravitational potential and the gas velocity from H1 and 2 observations, and we have radio polarization observations at short wavelengths, and here we have polarized intensity, and we can see the enhanced magnetic field in these downstream regions, and we don't have the total intensity there, but we do have some enhanced total field in the arms and bar of the galaxy as well. So this, what can we learn about these with if we take the observations and then try to do some hydrodynamics and other things and modelling, and then can we reconcile this with radio observations with all of these other things, and then can we learn anything about the cosmic rays as well, because that's what we're talking about here. So, modelling. Well, firstly, Lindblad et al. In '96, they took all of these nice observations from H1 and 0, and they can derive a bar and spiral rotation curve. And then they take as many of the parameters in this hydrodynamic model, this thin gas disk model, and then they try to fit as many of these as they can with the observations, and then try to run these things, and then there's some less well-known parameters, fine-tune them, then look to see what they come out with. And density corresponds to, for example, this H1 column density, and you can see that the density structures that they get in the models fit quite well with these grayscale density approach here. So it's kind of a bit of an iterative process, but eventually you get something which is kind of qualitatively nice and there's no best model, you just take the best features. So what we did is we took some of these input deduced rotation curves, and then we modified them and refined them, and then tried to also reconcile these things. Here we have just show you the detail of the velocity flow that they obtain. This is the bar, and it's in the frame rotating with the bar here, and with these strong shocks here in the bar, the velocity field. So we obtained something similar to this in 2D, and there's other hydrodynamics and smooth particle hydrodynamics that can all kind of reproduce this kind of structure. So what we did then is take this hydrodynamic velocity field and density field, and we put it into this Dynamo equation. And so we have the interstellar turbulence here, and we parameterize it in this alpha here. And the alpha is chosen such that the dynamo will saturate, and eventually there's a steady state of the magnetic field. So this happens by alpha quenching, and to go from this 2D hydrodynamics, we project this 2D density and velocity into a 3D Cartesian grid with this scale head in here. And then when this whole thing's saturated, and we have a full 3D magnetic field for this particular galaxy. So, yes. That's something up? Okay. Right, so then
is this pumping that you mentioned yesterday.
Yeah, no, but the form of the equation more.
Yeah, what's your pumping now? Again?
one is one. We need both. We need either between the two numbers and also 1/2 grad meter. Both.
Okay. Right, so then we have this magnetic field configuration. As I said before, we have these radio observations from which we can deduce the magnetic fields, or we can have this polarized intensity. So what we do is we make these synthetic radio maps from our magnetic field. So we calculate this Stokes parameters Q and U from the dynamo simulation. But there's a few things that we don't have directly, and one's this, cosmic ray electron density and its spectral index. So we don't have the distribution for the cosmic rays, distribution function for the cosmic rays in the galaxy. So that's one thing. And we don't have the thermal electron density either, but we can scale that. So we assume a power law for the distribution function of the cosmic ray electrons, and we just fix this to be constant, but we can change it and fix some value. I mean, can we do much better for that? No, I don't know. So this thermal electron density, we scale that with the gas density. We just assume the gas is photons, and then we take it to be some fraction of the photon density that we deduce from the hydrodynamic gas density. So then we need to make a choice for how we pick the number density of cosmic ray electrons. So of course the simplest choice is to just pick it to be a constant, and for us it seems to work quite well, but I'll show you that shortly. But then come to these equipartition assumptions in the energy in the cosmic rays and in the field. So we tried at least a few different things. One is we just take our field as it is and assume that the density scales with the magnetic energy in the field. But of course we don't have the turbulent field, and it probably depends on the total field. So we bring this in from the turbulent energy, which should be similar to the energy in the turbulent magnetic field, and we can deduce this from this turbulent energy or the polarized intensity, the actual observed value. Also, there's information in the total intensity, the total observed intensity, so we can take this intensity and then we should have some information about the total field in this, and we can try scaling it like this and projecting it into our data as it should appear in the sky. That's what I mean. So this was kind of the first attempt to try to make something that looks a bit like a radio map. But I mean, here we just have our density, which is this grayscale, and which is the 2D density, and then it's projected, and then it's rotated so that it's in the plane of the sky, and then we just average through this disk. And we have also our averaged field components in the plane of the sky, and then these contours of this polarized intensity, which is the thing we're interested in. And here's the observed one, and here we have the optical image we saw before. It doesn't look as nice as the colour one, but still. And we have these B vectors, which should suggest where the large scale field is. So this looks difficult because we have all of these contours and all of these different features, and it's difficult to say how it looks good, or how to even sometimes have to scale these contours because of the almost arbitrary units of the polarized intensity that we're using, and then there can be more effects due to, in the real observations, due to beam effects and etc. So we don't have these things. So what we decided to do was take cuts through these plots. So first we took a one just the north south, not this one south, cut straight down here, and this is how it looks. Unfortunately, they're not on the same platform. So we have the same central backroom in roughly the same place, and we just this produces minimum and maybe not so much as maximum. But I don't know, this still looks quite not too bad. But then we tried something else. We tried this other cut in the west-east direction, and here again we have this central peak in St. Blaise, and we seem to get this minimum here. Well, here, this one certainly looks in about St. Blaise, and this here, and also this ratio of these peaks looks quite good as well. So that one. We also decided if go here, we wanted to see how these arms look. So in the original frame, which is, we took a diagonal in the original computational frame, which is actually in sky here, which is at minus 31 degrees, something like that. And so this one also looks not too bad. Seem to have some features here. Maybe not on the outer part, but I think some of that's towards the end of our computational domain, so I don't know. So, conclusions, well, the model is satisfactory and robust, and we get most of the main features, and the form of this alpha in our diagonal equation doesn't seem to affect the results too much, so this is good. And we understand what all of the parameters do in our modelling at all of the different places, and we get a quite realistic field configuration for this galaxy. So with cosmic rays, the best model that we seem to have is this constant, which is the one I've just shown you. And after the weather, I mentioned that, but that was the best model with the constant. And the other models that we tried with the competition, well, we get some of the features, but the cuts don't fit anywhere near as well. So if this is the case, then this has implications for cosmic ray confinement. And are there any equipartition between the cosmic rays and the field? And it seems perhaps not in here, but who knows? And well, is it unique in this respect? Well, I don't know about so many other galaxies, but in the case of the Milky Way, I think we may have saw this plot earlier this week, where this cosmic ray density formed gamma ray sources, and it looks fairly flat, and then there are various ways that people try to measure this magnetic field as a function of the radius out in galactic center, and most of these things vary like this. So over from 5 to 15 kiloparsec is about a half. So you would expect that this cosmic ray intensity would vary by about a factor of 4 or something, but it doesn't. So I don't know. So maybe you can reconcile it somehow, but I don't know. But if not, then is this assumption really a dangerous assumption? Because the estimate here is probably 30%, but not 200% or however much it seems. So is there really a problem with using this for radio observation? So anyway, thank you.
Any questions? Yeah, what were the actual values for the difficulty and the alpha? What you assumed?
Maybe did you system about David, or
I'm sorry, I missed the question. But what was the actual values for the alpha and the difficulty?
The waste difficulty was on I think 26. We had some relatively increased 5 times, I think the same one, maybe 10 times some of the halo. And we also had an additional contribution of diffusivity portion today in the towards far out.
The centering along the bar.
Yes, sorry, central bar maybe.
was enhanced with velocity shear. I think here the diffusion had a component that scales with the velocity shear.
Yeah,
This really was important in order to get a good fit to the oscillations.
yeah, we found that in the previous model of intercell, was it 1097?
That it is very important to take into account the evolution of such structure as galaxy, and it is much easier than to get magnetic arms between spiral arms and bar. Evolution is very crucial.
There is no evidence of any displacement in this particular galaxy. Yes, and it's more or less steady. There is no reason to believe that it evolves. So, yeah, but for this galaxy, the dynamo model seems to work okay. So.
It is well, 10 years. It's
The hydrodynamic model in this case is steady, and I propose the ones that
no,
you
of course, but magnetic arms survive much longer than they should.
If I saw these pictures for the polarized, they were in the model, they were missing some structure. Yes. In the observed, there were also in the outer arms there were some more structure. What I think is some additional vertical velocity or some effects due to small diffusivity.
Of course, it's a model. Of course, our velocity field, however realistic it can be, it's still a model. It's a smooth version of the velocity field in the gas.
I mean, there was also a technical point that we modelled only the 15 kiloparsecs in radius of the galaxy. The galaxy is actually not a large one, so we didn't go a long way outside the bar region. And the zero band emissions and things, so we don't expect to produce pictures right at the edge of that
Short position polarization, that's different shekels.
As we see, we've got a small region, so we get with enough resolution.
The next, yes.
Velocity in that direction
How much agreement do you have on the, if you compare just the column densities, how much
Oh, the column density, well, with this density, you mean? With this density? Well, this is the same, almost the same density that I showed earlier with this H1, with this density contours on. I mean, it's similar because
It's true.
I mean, I don't have exactly what we have our model, but I don't know. But certainly we try to refine this a bit, so it should be at least as good as this, I hope. And we have a high resolution, extremely high resolution in 2D. So, and then.
Is it face on? Do you know the inclination?
Oh, you mean, well, this is projected into the
Do you know
into the sky.
How
5 degrees.
How do you know?
There's a
What
4
is
degrees.
really well known? How do you get it?
Inclination, yeah, 5 degrees per
Well
length.
done.
I think that it is really crucial because also 3D
Well, this is what we have. But the range is not 2D. That was compared
Yeah.
to the range.
Your machine is circular somehow. How do you know the inclination?
I think that the main method is to assume its shape.
Sure.
With variance it's more difficult, but I am not prepared to answer this immediately, but observers are more confidently say that its inclination angle is 25 degrees to the left.
I don't understand why you don't model in 3D.
It's modeled in 3D. We turn the data.
Okay, and then you can put also on 3D velocity field
This is what we do.
to the magnetic field.
This is what we do. Yes, this is what we do. But we present the observables in the plane of the sky as observers do. We cannot perform better than a telescope at the end of the day.
No, you make map from 3D map.
This is what we do. Yes, sir. This is that one. Yes, this is that one.
And except that velocity field is in 2D only.
Oh yes, originally yes, the mean clouds and the Natura, they modeled this galaxy in 2D. Yes. But then it should be a high resolution simulation of this galaxy. Because they wanted to capture all these shock fronts in the bar to measure the inflow rate correctly to simulate, because it's a crucial problem here, the resolution in the simulation of bulk galaxies. Nobody can afford realistic 3D simulations of bulk galaxies of the quality we need for this simulation. 2D is the best power can do. Maybe not, but it's complicated. So.
I have a comment.
Even physics is complicated.
Alpha effect. There are maybe 10 computations of the alpha effect in galaxies, and not even one led to the result that the alpha is a scalar. It is more dramatic. The alpha set was always negative when the alpha phi is positive. That means the tensorial character of the alpha effect is very strong. But, of course, for alpha omega dynamos it's not so important. But alpha omega dynamos, this was the discussion yesterday, always lead to very small pitch angles. In the alpha square omega regime, after our experiences, the tensorial character of the alpha effect is not very strong, but it is strong. And if you have some detailed comparisons with the observations, then I'm not sure whether it's allowed to work with a scalar alpha. The alpha is even negative. There's not even one simulation of the alpha effect where the alpha set has the same sign as the alpha phi. Not even one. All Katja Fayer, all the simulations see like this is what I expect also from you. And you have it, yes. So, of course, for a single alpha omega dynamo, it is not very important. But for alpha square dynamos in spheres, it is dramatic. It has a dramatic consequence. This tensorial factor.
But it's not a sphere. It's not a sphere. It's a disk galaxy.
Yeah.
Where velocity shear is enormous. It's the gravity field.
Yeah.
It's very. Can you show the next slide?
No, I believe it. I believe it. But for the discussion of the pitch angle, if the pitch angle.
We are not discussing pitch angle. There's nothing. Pitch angle is meaningless for bulk galaxies.
I agree with
Can you? Yes.
I mean, all that is extremely totally dominated by velocity shear. You can take the alpha effect away. I mean,
Velocity shear is just enormous.
Yeah.
And then magnetic field is completely controlled by the velocity field. Magnetic field is very closely aligned with these streamlines in the rotating frame.
Yes, I see. Yeah.
So alpha plays no role whatsoever. In alpha effect plays no role, or virtually no role.
For the dynamo.
It only supports the field from decaying. But the structure of the field is fully controlled by this velocity field. Because velocity shear is enormous in bulk galaxies. So the alpha effect only maintains this field against decay. But the geometry of the field is fully controlled by this well-understood velocity field, which is excellent news.
Yes.
However, you mentioned 10 models of alpha in galaxies. I would be happy with one, but convincing one. Therefore, it's not good that you have too many models of alpha effect. I would prefer one convincing one.
This is unfair.
But
There
anyway.
are many people who are computing the alpha tensor in the turbulence.
And still there is no clear
Yeah, this is your
answer.
private
What
view.
is this?
This
right?
is your private view.
But this is independent of the form of
Increasing accuracy. And there was no simulation with an alpha scalar. Not even one. Maybe all the people are wrong. And you are right.
But the accuracy of
It
these
is not excluded in
models is intrinsically plus minus 30%. You cannot achieve better accuracy in making models like this.
Yes, you can.
This conservative structure of alpha can change the result by
You must,
9%.
it is not necessary to accept
Globally,
simulation.
1%.
But the comment is all the simulations lead to one and the same result. This is no scalar alpha effect exists in the universe.
Yes.
No, only in your
Gunther, can I
concept.
do not
exercise my...
What are the consequences of that?
This is a good
We're going down in circles here.
Yes.
I'm going to exercise my province and make one final comment and then we go on to the next speaker. The comment is that you get almost the same topology of the field if you take the upper effect away completely and you just have a kinematic effect. All the alpha does is stop the field decaying. In this case, you may or may not be correct in normal galaxies. In this bar galaxy, is naturally alpha effect is with tensor or not limited relative. So, thank you, Andrew. And the President. Now just going to talk about, this is really Newcastle days, using radio observation to test theories of cosmic ray propagation.
I'm still part of the German
Yeah,
scientific establishment. Sorry, well, I don't know why my laptop is being rebooted. When I sent the title for this talk to Axel, I just got back from holiday, and I was obviously fantastically enthusiastic about this. Because when I looked at the title of the talk again when I came to prepare it last week, earlier this week, I realised I claimed rather too much to be confronting theories of cosmic ray propagation with radio observation. This is what I would like to do. What I'm going to do is see whether the best quality radio observations I have of an external galaxy tell us anything about what the theories of cosmic ray propagation are like. Can we test any of their qualities? Because I found immediately this is a fantastically difficult field, because the theory of cosmic ray propagation is like at a level way up here, and you have textbooks full of theoretical derivations of distribution equations and so on. And the level of observations of external galaxies is like at a level way down here somewhere. So I'll be comparing kind of a zeroth order theory with the observation of
Where is that?
That was Helsinki.
Which one? Yeah, Helsinki.
Yeah, very generously paying me for a short time.
Yeah.
So this work I was doing with Rainer Beck, and this is really just the beginning of stuff that we want to do. And I sort of have a bit of trepidation now, because I think I might be leaving myself open to some severe criticism for theories that I don't really fully understand. And I was digging around for a long time to try and find a kind of coherent picture at a very low level that I could use to compare with their observations. Because normally, this is a picture of M51 from the Hubble telescope. It's just, it doesn't come out so here. It's actually a fantastically beautiful picture from the Hubble telescope with calendars and all sorts. And on top of that are contours of total radio emission. And these kind of pseudo-vectors show orientation of magnetic fields. And what we've normally been doing in the past is really trying to interpret the polarized component of this radio emission and trying to figure out what that tells us about the structure of the large-scale magnetic fields. But this radio emission, a large part of it, is synchrotron emission. So it's coming from cosmic rays. And so we should be able to learn something about cosmic rays in these systems as well, if we develop the right techniques. So the outline of my talk, I'm going to give my version of basic theory of cosmic ray propagation. And then I'll talk a bit about spectral index variations, because this is, to me, it's the key measurement we can make in these external systems to try and learn something, and to try and test some theories. And at the very end, I'll make a brief comment about what the effect of having a strong mean magnetic field is. And all of what I'm talking about is just to do with cosmic ray electrons, not about the protons and heavier nuclei that carry most of the energy. Most of the energy densities made up of these heavier particles. So try and remember that I'm only talking about the electrons in this context. The radio spectral index is the key thing. If you have a power law distribution of electrons creating a synchrotron emission, it means you end up with a power law of synchrotron radio intensity in terms of frequency. So if you plot the log intensity against log frequency, you get a nice straight line. And for me, the simple way that I want to use our observations is to see if this frequency spectral index changes with position in an external galaxy. Because if you have high energy electrons moving about, losing energy through synchrotron radiation and inverse Compton scattering and other methods, these high energy electrons will start to emit at lower frequencies, and we start to see a steepening of the radio spectral index. Or alternative way of looking at it is, if these high energy electrons can leave the system faster or preferentially compared to low energy electrons, you'll also see a steepening of the spectral index. And so the energy loss mechanisms can be due to ionization, Bremsstrahlung, and adiabatic cooling, and these all have a weak or almost constant dependence on the energy of the particles. For our purposes of this talk, the main energy loss will come from synchrotron radiation and inverse Compton scattering that depend on the square of the energy of the electrons. But then also there's the possibility that the diffusion of electrons depends on their energy to some power also. So the high energy electrons can leave the system faster than low energy electrons. And this can write down a diffusion loss equation. This is one that I got from this book by Longer on high energy astrophysics. And this is the level that I could try and understand the theory. I couldn't go beyond this in terms of trying to find something that I could compare with the observations that we've got. Even though, like I said before, these are the best quality observations we've had for a long time, I think, and there's some room for improvements, but not much. So that how the number of electrons in a given energy range varies with time depends on the energy losses, which was on the previous slide, which is just all piled up now in this term B. It depends on the sources, this term Q, and it depends on some diffusion coefficient. And so next I'm going to consider a really simple system where it's a steady state, so this is set to 0, and we're not worry about diffusion at all, we're just considering energy losses in a really simple steady state condition. Then you can solve with a very simplified version of that diffusion loss equation and see how these different energy loss mechanisms will affect the synchrotron spectral index. And so the ionization losses, which I say will not be important here, will lead to a slight flattening of the synchrotron spectral index. The Bremsstrahlung and adiabatic losses will lead to no change in the synchrotron spectral index, and these synchrotron and inverse Compton energy losses will lead to a steepening of the spectral index by a factor of about half from this very simple version of it. Solving the diffusion loss equation. I'm less certain about this at all, and I'd be really interested to get some good references about why I can learn more about these diffusion losses. But from what I could figure out, if diffusion losses dominate, I expect the synchrotron spectral index to steepen by amount delta over 2, and this delta is the power that the diffusion coefficient was depending on in the previous slide. So that's my simple version that I have in my head at the minute of the theory that I can attempt to address. This is a spectral index mark of M51 between the frequencies of wavelength 20 centimeters and 6 centimeters. The resolution here is 15 arcseconds, and that translates to about 700 parsecs in the disk of M51. And this is the size of the beam as well as the map. It's half of one of these intervals on the y-axis here. So it's a quite high resolution map. The contours that are on here in black are from an H-alpha, hydrogen alpha map that shows where it's from for every emission is. And these contours show the positions of the spiral arms in the galaxy. So you see it's a very strong 2-arm spiral system. You've got one arm going around here, and you've got another arm going around here, and then this is some companion galaxy it's called, but it's actually quite a long way behind M51. This is the total radio spectral index, so it includes thermal emission as well as synchrotron emission. And so at 20 centimeters there's probably not very much thermal emission, but at 6 centimeters there can be quite a lot. It can be 30–40% in the spiral arm regions especially. Fortunately, you know
So the spectrum can be flatter, synchronous spectrum can be flatter than implied by this.
It can be steeper. I should have mentioned this before. The thermal frequency spectrum is known, and the thermal spectrum goes as frequency to the power minus 0.1. So the thermal emission gives a very flat spectrum, and the synchrotron is steeper. So, for example, these points here and here, these dark points, these are H2, massive complexes of H2 regions forming a lot of stars. There's lots of emission in the hydrogen alpha map, and these regions have spectral index of about 0.5 or flatter. Now, most of that is coming from the 0.1 thermal spectrum, and then some of it, the steeper bit, is coming from the synchrotron. And it's very difficult to make this separation, and I'm not going to attempt to make a separation across this whole map into the synchrotron and thermal parts. That's something for the future. I think there's some possibilities of doing that now. But basically, you need to know how dust extinction affects a thermal emission map like hydrogen alpha. And this is a tricky thing. But what I do know is in these interarm regions here and around here, you can see immediately that the spectral index is much steeper. So in these interarm regions, here, the spectral index is like -1 or steeper. Significantly different to the spectral index in the arms. And also there are low-level contours of thermal emission in those regions. And I can use those low-level contours to set a limit on how flat the synchrotron spectral index can be, because if I make it too flat and then separate the total radio map, I end up with no thermal emission in those interarm regions. So around here and around here. So I can use that to set a limit in the interarm regions of how steep the synchrotron index has to be at a minimum, and it has to be at about -1.1 in this region here and in this region here. Otherwise there's no thermal emission left in the radio when I do the separation, and I know from H-alpha observations that there is thermal emission there. So to summarise down the right hand side here, in the interarm regions the spectral index of the total radio is somewhere between 1 and 1.1, and I think that I'm certain that the synchrotron index is down definitely at 1.1 and maybe even a bit steeper. I can be sure about that. In the arms, the total synchrotron spectral, the total radio, not the total radio index, is varying between about 0.5 and 0.9. But that's strongly affected by thermal emission, and I can't use the same type of method to try and put any limits. Really need to make some extinction corrected H-alpha maps to try and independently set a limit on thermal emission. But I think it's fairly well established. If we believe that supernovae are the source of the cosmic ray electrons, I think it's reasonably well believed by people that the injection spectrum in frequency domain will be somewhere between 0.5 and 0.6. I think that means that in the energy spectrum, the spectral index will be 2.2 or 2.3. I think this is the correct relation. So now, these supernovae are in the arm, roughly, located in the spiral arms. And you're injecting, and they're putting in electrons that should originally have a spectral index and synchrotron emission of 0.5 to 0.6. By the time these electrons are getting into the interarm region, the spectrum is steepened by quite a lot. And I think this is because the electrons are losing energy due to the synchrotron and inverse quantum masses. I don't think it's because they're diffusing out of the system with this energy-dependent diffusion coefficient so quickly. The difference in spectral index, I think, is about 0.5. Well, this can be better defined. And I mean, I'm waving my hands a lot in these things, but I think that the difference in spectral index and the synchrotron emission would be about 0.5. And for diffusive losses, this basically means that the diffusion coefficient has to go with the energy to the power 1. And from what I could figure out, what I could find in the literature, this power delta is expected to be between something like 1/3 if you have the Kolmogorov spectrum turbulence, or 0.6 based on some measurements in the heliosphere. So this is quite a strong dependence on energy that would be required for diffusion to explain the steepening of the index. And I think this is because in M51 you have very strong magnetic fields. And I mean, this is a map of the magnetic field strength in M51 based on paper equipartition estimates. And the fields are strong. I mean, in the spire arms you have fields of about 25 microgauss, and in the interarm regions even you've got something between 15 and 20 microgauss. So in this region where the spectral index is steepening between the arms and the interarm regions, you've got a magnetic field of about 20 microgauss. So in that type of field you can estimate the lifetime of a synchrotron electron. So in a field of 20 microgauss, an electron 5 gigahertz, that's 6 centimeter wavelength, would have a lifetime of about 5 times 10 to the 6 years. And that's just from synchrotron losses. There will also be, in this domain, energy losses due to inverse Compton scattering. And this, in the Milky Way, I think the inverse Compton losses go with the energy density of the radiation field. And in the Milky Way, I think the estimates are that the energy density of the radiation field and the magnetic field are at least the same order of magnitude. Maybe there's more energy in the radiation field. So with inverse Compton losses going in, this time scale will reduce by a factor 2 or 3 or whatever also. This is not a very useful estimate. Basically, this should be less than. The output speed has to be less than 200 kilometers a second if they're going to go about 1 kiloparsec from the arm into the interarm. So the region over which the spectral index was steepening strongly was about 1 kiloparsec. But that isn't very useful, but maybe this is.
Why is it so large?
So large.
So large. 200
Less. I should have wiped this out last night when I thought more about it. If they go any faster than this, they're going to get into the interarm region before they've lost their energy according to this time scale.
Yeah,
this is all it is.
1 kiloparsec.
L is 1 kiloparsec. The lifetime is this one that I just said.
And the diffusive length is also, with this time scale, is also 1 kiloparsec.
Yeah. So I think this is not useful. The only thing it could be done, if there is an independent estimate of the density, then you can, if we know the magnetic field, then you can really see whether this is reasonable or not. I estimated this because of the idea that the particles propagate at full speed at alpha velocity, and I just wanted to see what this might be. But since this is less than, it can be anything less than.
So, sorry, but I probably missed something. But in this time, 5 million years, the particles can diffuse over 1 kiloparsec. This means that they can safely leave arms and radiate their energy within the interarm space.
This is the time for them to lose their energy by emitting synchrotron radiation.
Yes.
It's nothing about diffusion.
Oh no, but in this time they can diffuse from where they've been accelerated in the arms to interarm space.
Yeah, this is
They have enough time.
The next, this is more useful estimate. What is the diffusion coefficient if these particles have to diffuse 1 kiloparsec in their lifetime? And then the diffusion coefficient for these 5 gigahertz 6 centimeter electrons is 3 times 10 to the 28 centimeters squared. Now, I had absolutely no idea whether this was, when I calculated this earlier this week, whether what this was reasonable or not or anything like that. And then I just noticed in a paper of Mardenhamish recently, implementing cosmic rays into Zeus code, mentioning reasonable value of 6 times 10 to the 28. And
This is for the proton.
Oh yeah. And then I checked the reference that you give in your paper to Armstrong's paper, the Galcrop models. But so sure, this is the diffusion of the protons, and all of my stuff is about electrons. I now have no sense about whether this is really reasonable for electrons or not. I really, in the hands of the experts.
It only depends on rigidity, so it must be the same.
Right.
So rigidity, so it must be the same.
So I mean,
if it's electromagnetic process.
Yes.
Right?
So this is what I was really very pleased about. Okay, so now if people think that this is a reasonable value for the diffusion coefficient that's been estimated in the Milky Way, very sophisticated modelling, and this I've used the arguments just based upon the spectral index that we've measured in the nearby galaxy, and to estimate a similar scale of diffusion coefficient in an external system for the electrons. So things can be done much better, of course. Now, what about the mean field? Now, diffusion coefficient that I saw had no dependence on whether it's diffusing along the field or across the field lines. and from the arm into the inter-arm region in M51, the diffusion would have to go across a large-scale field component that's about the same strength as the turbulent field component in some places, and in some places the large-scale field is quite a bit weaker than the turbulent field. But here in M31, it's another nearby galaxy, the Andromeda galaxy, where it has a fantastically irregular magnetic field. The regular field is the same size, the same magnitude as the turbulent field, over a huge distance that goes about 8 kiloparsecs in radius and right the way around the galaxy. And this is a map of the total radio emission in the colour scale. And this is a ring that's centred at about 10 kiloparsec radius. And these little vectors are showing magnetic field. And by some much more clever and sophisticated modelling than I've been discussing with the synchrotron spectral index, we've interpreted this and the Faraday rotation using several frequencies and so on. This is a fantastically regular magnetic field in this region that extends over 6 kiloparsecs in radio scale. It isn't a circular magnetic field, it isn't just a toroidal, purely azimuthal field, it's a spiral that's very tightly bound with pitch angles of about 10 degrees to 20 degrees.
So it's a tube here, it's not possible.
It's a spiral, it's not a tube. It's a spiral. It's very highly inclined. I mean, you really have to see it face on. This is inclined at about 78 degrees.
It should be helical as normal.
Yeah, these are sampled on huge kiloparsec scales, you know.
Medical planning makes such model. Helical fields is quite here, but that's.
This we have better data. I'm aware of what narrative. Anyway, it has a very strong V magnetic field that is very highly azimuthal. And there's always been a question about why the radio emission, why the synchrotron emission is confined to this ring, and why you don't see anything at shorter radius inside, and why you don't see much outside. Because there are indications that the magnetic field exists in these regions here. And there are indications from rotation measures of background extragalactic sources that the magnetic field of Andromeda is, there's some observations that are consistent with this type of model of magnetic fields that are at greater radii as well. And from the work that we did, we saw that the magnetic field profile in radius is really quite flat. So if you look in radius, and this is the regular magnetic field strength, you get between 6 and 14 kiloparsecs, you get this, it hardly varies at all, it doesn't have a sharp maximum. Whereas the synchrotron emissions have a much sharper maximum as you go across here. And I think it can be maybe an indication that the cosmic ray electrons are just propagating preferentially along this ring and they're not propagating across the line so easily. And that the cosmic rays are being confined by this very regular magnetic field where the regular part is the same strength as the random part. And we're making more new observations now of particular regions of this galaxy to look to get good measurements of the spectral index, to see if the spectral index is steepening as you go in cuts like this across the galaxy. I think it can be indicative of better sign of this. So for the future, it would be good to have, like the map I had of M51, spectral index, total radio spectral index, have a map of the synchrotron spectral index. And to do that, we need to make an independent estimate of the thermal part, the Bremsstrahlung part of the radio emission. And I think this can be possible. The dust extinction in H2 regions is quite well known now with some recent observations that people have made with the Hubble telescope and things. What is just an open question is how much the diffuse ionized gas in galaxies is suffering from dust extinction. Breaks in spectral index I haven't mentioned, but if you observe lots of frequencies, it might be possible to see where there's a break in the spectral index. I won't talk about any more about that. And obviously, what we need to do, what I'd like to do, is much more. Some modelling, basically solving the diffusion loss equation and model of that galaxy to see what kind of distribution of spectral index it gives. rather than just looking at orders of magnitude differences between points separated by a kiloparsec, but do something a bit better. But I kind of had to start from some estimates to see whether it was worthwhile pursuing this or not. And then in the case of M31, maybe it's possible at some time to get estimates of at least the relative magnitudes of these diffusion coefficients along and across the field directions from observations. Oh, no, I shouldn't have. I wasn't meaning to put this. This is another nearby galaxy, NGC 6946, and this is again a total spectral index map, going in the same range of scales from sort of flat minus 0.4 down to steep 1.1. And you can see it's another galaxy where there's strong variations. This doesn't have such a strong spiral pattern though. That's why you don't really see the spiral arms.
Well, still is all of them, the main two ones, you can see them in red.
Yeah, right. This is one arm where you have lots of thermal emission here, and here H2 regions, it's flat spectrum, and then here it's around you got steep for sure. It's just not as pretty as M51 because the spiral is a bit more.
But still, there are also visible in here, amazing.
So I think this M51 is not a unique case. Also.
Thank you, Andrew.
Have any questions?
Did you try to make the estimation of the last point you mentioned about the ratio of the perpendicular to the parallel coefficient?
Not yet.
You think it is difficult, so can we expect soon?
Yeah. Well, we want to see if we can see spectral index steepening going across the direction of the field compared to the lock. We've got the observations are happening. We just need to reduce the data to measure this. So the data has been taken. So I think that it is possible. I don't know. I mean, I need to get some idea whether it's worth it or not. Because if people think these things are already established, then I've got other things.
I'm not sure if it is established. So.
But do you mean to do it in M51 or M31?
M31, because you know it has this very regular field, and so
almost as in UFO, so it's convenient.
Yeah.
It will be very important for this for
We will hope it. Right.
Can you be sure at this stage that the arms aren't flat just because of the thermal emission?
Yeah.
Thermal emission in the arms. So
For sure, yeah.
It must be flat.
Of course, yeah, they are flat.
So you can't explain the spectral index difference just by the thermal emission?
No. In the inter-arm, I'm very confident with the synchrotron. And in the arm, I would say, well, if you believe that the supernova are injecting.
No, ignoring that.
Okay.
Just from the observations, can't it just be because we don't know what the injection is?
I mean, yeah, it could be. It could be, yes. So that's not. I couldn't rule that out. But then if you want to have a constant synchrotron spectral index in that galaxy, it has to be a very steep one. It has to be 1.1.
In our galaxy, it's also about one of these features, the spectral index. It's about one.
When people have been measuring in external systems, global spectral index, they usually like about 0.8 or something like that. 0.85.
Yeah, but it's not so flat. Yeah. But in the future, will you really get a pin down
Yeah.
the thermal?
Yeah.
So I have to.
This is, I'm pretty sure, because the extinction of H2 regions in that galaxy has been measured. It's just a question of using that. And there's a problem with how much the diffuse gas is suffering from extinction, but for the arms that doesn't really matter. It's really, you just want to make sure that you've got a good correction for H2 regions. And I think that we can do that. We can at least make the first attempt to do that. So I would say yes, we can really get a synchrotron index for the arms reliably.
But it's still quite a big correction.
Well, I don't know. I mean, until you try it. I mean, it might not work. It might just. We actually to try it. In the past, people have made their separations always by assuming constants, and I've never been happy about that. So I'd like to try something different.
But still, though it's assuming it's not, did it work? Was there still some steepening seen as a result?
with old subtractions of thermal.
The old way of doing the subtraction is to assume the synchrotron spectral index is constant. So you immediately throw away everything that you want to know about cosmic rays. People do that because they want to again make magnetic field estimates and things like this. But they're never very interested in cosmic ray stuff.
Any questions?
Are also plans to do that for edge-on galaxies?
So I was wondering if people would be interested in edge-on galaxies. It's not really my thing. I've not observed them. Yeah, there's a student in Bochum who's got what could be potentially excellent observations of NGC 253, I think, where it might be possible to see spectral index variations.
891.
It's hard. Edge-on galaxies is just very hard observational because you've got this very bright disk and then you've got a very faint emission. You want to measure the spectral index of the faint emission and the disk. It just creates instrumental problems. But I didn't mention. I mean, the maps that I show don't suffer from any problems like missing spacings and interferometers. That they are observations with BLA merged with single-dish observations. So all of the flux is there. This has been another problem in the past if people are looking at spectral index. It's very hard to get consistent observations at a set of frequencies that aren't suffering from one problem or another, and we've got to that stage.
Anything else? Questions? Okay, well, we should thank trustees for this morning's session.
Very interesting.